Go for it.
Hey, our next speaker is going to be Amanda Bienz, and to be talking about RAPtor, a parallel algebraic multigrid solver with reduced communication. And take it away.
All right, thank you. All right, so I'm talking about RAPtor. It's a code base we wrote for parallel algebraic multigrid with reduced communication costs. This is work done with my advisor, Luke Olson, and also with a lot of collaboration from Bill Grob. So there are a lot of solvers currently in production. You can see on the left here, Cusp and AMG X are used for GPUs. PyMG is often used to solve in Python. And then everything else on this slide, they are distributed solvers used in MPI. And so Boomer AMG from Hypre, ML from Trillinos are two really common ones. There's also a package in PETSI, and then the other three are European packages. So why create another package when all these exist? The reason we made RAPtor was so that we could switch out the way that it's communicating very easily. So we can stick in a different type of communicator to change how MPI is acting throughout the solve. So that was really our main motivation for it. We tried to make it like PyMG in style so that it should be very easy to go from Python to parallel programming if anyone wants to. So an outline of the talk. First, I'll give an overview of AMG, and then I'll talk about communication inside of AMG. Then I'll talk about node-aware communication. This is the main reason for creating RAPtor. Finally, I'll talk about a few other methods very quickly for reducing communication in parallel AMG, and then finally some comparisons with Hypre. So what is algebraic multigrid? It's an iterative method for sparse linear systems. So as with all iterative methods, you have a problem, ax equals b, and you start with an initial guess to x. So if you look at the error in your initial solution with that initial guess, it's going to be very all over the place, like the graph on the left there. So that figure you can see is very high frequency, the error's kind of all over the place. So relaxation methods are really good at getting rid of this high frequency error. So a few methods of either Jacobi or Gauss-Seidel, SOR, will give you, a few iterations will give you the smooth error that you have on the right. So you can see you still have a lot of error remaining. If there was no error, this would just be a flat blue line. So you do still have a lot of error. However, it's very nice and smooth. And so this is called low energy error. So once you have this low energy error, relaxation no longer works so well. It's essentially averaging neighboring points. And so when they're all very similar, it takes a very long time to get rid of that error. So the idea of algebraic multigrid is that we want to take this problem and restrict it to a coarser grid. And then on the coarser grid, you can see this bottom figure, the error turns back into some high frequency error. So it looks more jagged again. So you can once again use a relaxation method on this to smooth out that error, then restrict it again, and continue this process until you get to a level or a grid that's small enough that you can solve for the error directly. And then once you solve for that error directly, you can interpolate it back up throughout your hierarchy. So there are two parts to this. There's the setup phase, where you create this hierarchy of coarser and coarser grids, and you also create the transfer operators, so getting from a fine level to a coarser level. And then there's the iterative solve phase. So this is where you do this process of relaxing and then coarse grid correction. So I'll talk a little bit more about those. So the setup phase. The setup phase of AMG, you start with your initial system, ax equals b, and then on each level L, you're going to create a strength of connection. This basically determines what part of the sparsity pattern is very strong. So you only keep larger value or edges that have larger values. And so you can see the first graph here is just a graph of the initial system for a very small problem. The second graph is a strength of connection. So you can see that this is anisotropic, so you only keep the edges in the direction of the anisotropy. Then you also have the CF splitting. This is where you split nodes of the strength of connection into coarse and fine points. The fine points are going to stay on the finer level, where the coarse points will go down to your next level. So the following level in your AMG hierarchy, the number of rows in that will be equal to the number of coarse points. Finally, you'll create an interpolation operator. So this interpolates between the coarse and fine levels. It's your transfer operator. And then you use that interpolation operator P to create your new coarse level. So the coarse grid operator A on level L+1 is equal to P transpose times A times P. So this is called the Lurkin product. It's a triple matrix product where all matrices are sparse. And so for RAPtor, we are only considering this case with the Galerkin product that's typically used for symmetric problems. It can still solve problems if they're unsymmetric, but they have their sparsity pattern is very close to being symmetric. However, if you're solving general unsymmetric problems, a lot of times you're going to choose a different restriction operator than P transpose there. All right, so the solve phase. This is similar to what I explained on the slide before with relaxation. For each level L, you'll start by relaxing the problem, AX equals B, and then you'll calculate your current residual. You'll restrict this residual to the fault or the coarser problem, where you do coarse grid correction. And this consists of doing the same thing again, so relaxing that level and restricting it and continuing that until you can solve for the coarsest level. Then once you have your error, you interpolate it back up to your level, and then you're going to improve your solution. So you add this error to your current solution X. So that's the general idea of AMG. Serially, it works very well. It's an O of N method. However, there are some problems in parallel. So what's the main problem with this? If you noticed in that V cycle before, if you look at the levels in the AMG hierarchy, each level is getting smaller in dimension, but the density is increasing. The number of non-zeros per row is even increasing. And so if you look at these three levels here, on the left, you can see that they get, the bands get thicker and thicker. And so you have a more dense problem that you're trying to solve. Serially, this is not a problem because the total number of non-zeros is typically reduced, and so the total amount of local work would be reduced. However, it does create problems in parallel. So if you look at the figure on the right here, this is just an example linear system that we've split across 4 processes row-wise. So each process here, P0 to P3, they each hold 2 rows of the matrix and the corresponding 2 rows of each vector. The matrix rows, the local rows to each process, are further partitioned. So if you look at the first 2 rows of the matrix here, there are 4 solid blocks. These make up the on-process block of the matrix. So these columns, to perform matrix operations, they're fully local. They correspond to vector values that are also stored on that process. However, we also have pattern blocks, or the off-process block. And these columns correspond to vector values that are stored in other processes. So if you think about doing a SPIN-B with those first 2 rows of the matrix, those first 4 blocks can just be multiplied by the local blocks of V and then added to the solution at W for those 2 local positions. However, all those pattern blocks first need to communicate to get vector values from other processes before that SPIN-B can take place. So the problem that we see with AMG is that if you get these coarse levels, you get that a larger number of non-zeros per row, you end up having more communication because you get more non-zeros in this off-process block. So that creates a lot of problems. And so if you look at the figure on the left here, this is the time in the solve phase of AMG spent on each level of the hierarchy. So level 0 is your original large matrix, your original system. And then every level after that is smaller in dimension. So ideally, we would like every level to take less time. But you can see around level 4, it really jumps up. It takes a lot longer than it did on the original system. This figure is also partitioned into each row, or each block is split into local computation and the MPI point-to-point communication. And so you can see on these coarse levels, almost the entire time is spent communicating with point-to-point communication. The plot on the right shows something similar. As you take a problem with 10 million degrees of freedom and you scale it out to a large number of processes, communication starts to dominate. So you can see that the percentage of time spent communicating increases as you scale the problem out. And so AMG tends to lack scalability due to these large communication costs, and they're coming from these coarse levels of the hierarchy. Yeah.
Are you reducing the process set at the same time that your course need is picked on, or are these communication numbers for the original process set with like 12 courses?
Yeah, they're with the original process set. We're not redistributing the problem at all. So there are a lot of methods for reducing this communication cost. You can alter the algorithm, and so there are a lot of alternate ways of doing it parallel AMG. You can use aggressive coarsening, and so when you split into C and F points, the C points go to the coarser level. You can do that more aggressively. So pick fewer C points with more F points surrounding them. So that means you'll have fewer course levels, and they'll be smaller in dimension. So it'll take longer to converge, but each iteration will be a lot cheaper. Smooth aggregation is a similar concept, that you find aggregates of nodes rather than splitting into C and F points, so you can, again, have fewer levels. Non-Galerkin and sparse Galerkin methods systematically remove non-zeros from the matrix if they're relatively small to add sparsity back in and reduce communication. And there are a lot of other ways to alter the algorithm. You can also alter the parallel implementation. So you can use graph partitioning and topology-aware mapping to reduce the number of edges split between processes and also reduce the hop count that messages have to go. You can repartition the matrix to later on in the hierarchy with this to rearrange and only use a subset of the processes. You can do a redundant course solve. So on the courses level, when you're actually using a solver like Gaussian elimination, a lot of times all active processes, you want them to all gather the full problem that's remaining, and each of them solves it independent of the others to reduce communication. So there are a lot of methods in existence. The main motivation for RAPtor, and what we're really looking at, is that we want to use the topology of the parallel computer to reduce the cost of communication throughout AMG. So the stuff we look at can be used in combination with all of these methods. So looking a little bit at standard parallel topology, typical supercomputers have a large number of nodes and each contain many processes. So on the left here, we have a really small example system of 6 processes distributed across 3 nodes. And then we split up our system correspondingly. So again, this is like the system before. There are 6 processes now, and so each process holds 1 row of the matrix. But we also are splitting this up across nodes. Some of these blocks are not showing up. So you can see that we have the solid blocks are still on process, so they're fully local. Next to some of the solid blocks, so right here, there's actually a very light block that corresponds to on node. And so it corresponds to a vector value that is stored on a different process, but that process is on the same node. And then finally, we still have these pattern blocks, but now they only correspond to off node. So if it's both off the process and that process is on a different node. So there are a lot of different ways to easily figure out which processes are on the same node. You can export environment variables. So this is the variable for Blue Waters to determine it. There's a similar one for Blue Gene Q machines. This just maps how determines how the processes are mapped to the nodes. So then you can figure out which ones are on the same node. So why is this important? If we look at the cost of communication, it really varies based on the location of the send and receive processes. So the on-node messages end up being a lot cheaper than the off-node messages. So if you look at this plot, the blue and green lines are for off-node messages. There are 2 different lines here. It's based on the max rate model that takes injection limits into account. And so if you're sending with less than 4 processes per node, you don't hit your injection bandwidth limit. But if you send with more than 4 processes per node on Blue Waters, you do. And so there's a distinction there. But regardless, or taking into account, we normally use 16 processes per node, there's a very large distinction between on-node and off-node. There's also a distinction on Blue Waters between on-socket, and then the red line is on-node but off-socket, as the on-node but off-socket does not share memory. However, we're not really looking at this. We're just looking at this distinction between on-node and off-node. So standard communication, if we have 8 processes distributed across these 4 nodes, and say they all want to send messages to process Q on node M, they're going to do so regardless of where they lie in the network. So each process gathers up all of its data that it needs to send to process Q, and it sends it as a single message. So you can see you have 4 messages here going through the network between these 2 nodes. Similarly, if you look at just process P on node N, and say that actually also wants to send to all these other processes on node M, it's going to do the same thing, gather the data that needs to be sent to a process and send it directly, because it's not paying attention to which node they're on. So not only do you have 4 messages going through the network here as well, you also, if you look at the data being sent, say these first 2 values are being sent to the bottom 2 processes, second 2 values are being sent to the top 2 processes. Not only do you have duplicate messages going through, you actually have some duplicate data going through the network and being sent through multiple times. So we would like to fix this because the off-node communication is so costly. So we look at a new algorithm for node-aware communication. If you're sending a message and it's fully on node, so these processes want to send to P, just send as you normally would, gather the data and send it directly. However, we're going to change how off-node communication works. So rather than gathering all of the data that goes to some process Q, these processes on node N are going to gather all data that goes to any of the processes on node M. It's going to gather all that data and send it locally to P. So P is going to collect all of that data, and after it does that, send it as a single message to process Q on node M. And then process Q will redistribute it to any of the processes that need it. So it's a pretty simple concept. So an overview of what the node-aware matrix operations look like. You have these three steps. So you redistribute the initial values, send them as a single message across the network, and then after you receive the values, redistribute them again. You also have the on-node communication, and then finally you have your local computation with the on process, the on-node, and the off-node locks of the matrix. Note that steps 4 and portions of step 5 can be overlapped with steps 1, 2, and 3. When we show results, we're not doing any overlaps. We're just looking at the speed up from communication. However, you can get additional speed up by overlapping. Local computation can be done at the same time as all the other steps. And once you receive on-node communication, you can do the work with that. Also note that we're assuming there are many nodes in the network, not just N and M. So node N, those processes might also send to some node O. They're going to gather them on some process that's not P. So maybe they all gather on this process below P. And then that process is going to send to node O. So all of the processes are still active in communication. This isn't some master process thing. So we do see significant speedups over using some master process. So if we look at the communication requirements when we use node-aware communication, this is just for doing a SIMD on each level of this AMG hierarchy. On the left here, we show the intranode communication, so fully local on node. And you can see that node-aware communication, you send many more messages on node. However, on the right here, we can show that we greatly decrease the number of messages that go into the network. Similarly, for the size of the messages, on the left, we show that we increase the number of, or the size of local messages, but we decrease the size that go through the network. This is looking at the max, both of these, we're looking at the maximum on any process. If we look at the total number, we see very similar plots.
Is there an obvious reason why these isn't monotonic in level in one way or the other? It seems kind of slightly surprising that somewhere in the middle is where the number of messages peaks.
Yeah, so it's because it's increasing in density. And so somewhere in the middle, you get these very dense levels, but they're also still large enough that you're talking to most processes. So our idea is that we want to add this node-aware communication throughout AMG. So in the setup phase, if you remember, the first thing you do is create a strength of connection matrix. That's a fully local operation, so we're not putting that in there for the standard AMG. However, we want to add it to the CF splitting, determining which points should be coursed and go to the next level. Also forming those transfer operators between fine and coarse levels. And then that triple matrix product called the Galerkin product, the sparse matrix multiplication, we want to add it there. And then the solve phase, we also want to add this, and every operation in the solve phase is just sparse matrix vector multiplication. So those are the components that we've added it to. If we look at how this affects the setup phase of AMG, these are the different parts of the setup phase. You can see that the strength, again, doesn't change because it's fully local. There's very little effect to the CF splitting. You get a little bit of speed up, but it's very minimal. Part of this is because the CF splitting is actually an iterative method. And so you're only communicating for rows that have not yet been determined as C or F. So because of that, we only implement this to the first iteration, which is the most expensive, but that yields pretty small speedups. And we actually see some slowdown for P transpose AP in this problem. But we did see large speedups for A times P and the interpolation, forming the interpolation operator. To clarify, A times P is the first step in forming P transpose AP to get your course level. And then after you get that AP, you multiply that by P transpose. These are actually different types of communications. They perform very differently. P transpose AP, the communication is based on the sparsity pattern of P rather than A. And you can also see that you have slowdown on the first few levels. So you still have this nice structured communication on those first few levels. And so you're not going to see speed up. And on top of that, you actually have extra steps here in synchronization, so it causes slowdown. So for this hierarchy, we are only looking at level 5 on. And that's the only time we use node-aware communication. So those first few levels, we don't use it. We do keep node-aware communication in P transpose AP because this really varies by problem. In a lot of problems, you do see a lot of speed up for it, but having the slowdown has very little effect. So we keep it in regardless. Looking at the solve phase, we see much better performance as the real costs are in this, or there are a lot of savings to be had in the SPINBs. And so you can see mainly in relaxation and calculating your residual, this depends on A, your larger matrix. So you can see really large speedups. In the middle of the hierarchy, we get a 25 times speedup. We also do see speedup in the restriction and interpolation operators. However, these depend on, this is P, and so it is a smaller matrix with a smaller sparsity pattern. So the speedup is less significant, but again, we do use the node-aware communication. Again, we're only using it on level 5 on, because we just set level 5 for everything. However, this is motivation because we could get speed up on levels 3 and 4, but we don't want to look at every problem before we figure out when to use it. And so this is some future work to figure out on the fly when it should be turned on and not. So if we look at the results, the timings from using this on level 5 on from the hierarchy, this is showing the blue line on the left is the setup phase, just standard. And the green line is with using this node-aware communication. So this is setting up a problem of with 10,000 degrees of freedom, or 10 million degrees of freedom. And you can see as we scale out, we end up getting significant speed up over the standard AMG setup. We actually also increased the strong scaling limit quite a bit of this setup phase. On the left here, we have the same thing for the solve phase. And so you can see, again, we do increase the, we do have speed up at these larger numbers of processes when we really strong scale it out, but the strong scaling limit doesn't get increased too much. However, one really important thing here is we're going to be running the setup phase and the solve phase on the same number of processes. You don't set up on a large number of processes and then solve on a smaller. And so because of that, we really care that these, at 4,000 and 8,000 processes, the time of the solve phase doesn't go up drastically like it does with the standard solve phase. And so if we look at the total time for AMG, we can see that we do increase the scalability to 8,000 processes, and we do have pretty significant speedups over the standard AMG. For this, we scale to 1,200 points per core, but we actually have scaled out farther to 16,000 processes. I just don't have runs that large for this problem. All right, so there are a lot of other methods for reducing communication. I went over a few of them at the beginning, but one of the main ones is aggressive coarsening. So it's a little bit difficult to see here the difference in these plots. And so because of that, I did point out the number of coarse points in each one. However, in aggressive coarsening, instead of looking only at immediate neighbors, you look at distance too. So you look at the neighbors of your neighbors. And so you form one coarse point, and then the neighbors of your neighbors are becoming fine. So you end up creating many more fine points. This becomes very obvious when you have a very large problem. And so your savings will not be 4 coarse points. It'll coarsen much, much more quickly. It actually is almost required for most 3D problems, if you're using classical AMG, to use aggressive coarsening. Otherwise, you tend to run out of memory. And then it also goes significantly faster. So we did test some 3D problems, mainly the 27-point Laplacian. And so for this, we use the aggressive coarsening. And we can see that we still see large speedups. The green is, again, using node-aware communication throughout AMG. We see large speedups and improvements to scalability by using this node-aware communication. Similarly, we also have the smooth aggregation solver. So we recently added this to RAPtor, like within the past month. And so rather than doing a CF splitting, the whole setup phase is a different algorithm. And so you don't form a CF splitting, the CF points. Instead, you form aggregates. And so you take a bunch of points and you gather them up, you like partition the matrix, and then each aggregate becomes one coarse point on the next level. And because of this, you end up having larger aggregates, and you coarsen much more quickly. And so for this, we again looked at the Laplacian problem, and we can see compared to Ruggie-Steuben, smooth aggregation, or Ruggie-Steuben is classical AMG. Compared to that, the smooth aggregation solver is much quicker. It does increase you need to do many more iterations. However, the iterations are so cheap that you see large speedups in both the setup phase on the left and the solve phase on the right. And so again, we wanted to see if node-aware communication further improves upon this, and it definitely can. This shows for both the anisotropic and Laplacian problems, speedups and extensions of scalability when using this node-aware communication throughout AMG. Finally, there's also sparsification. That's the other method I talked about, non-Galerkin and sparse Galerkin. We worked on a method that's similar to non-Galerkin coarse grids, and the idea here is that you want to remove relatively small entries that are outside of some predetermined sparsity pattern, and then you're going to add these values to the diagonal and remove them from their original spots. So you end up adding sparsity back into the matrix. Again, this affects convergence rate, but it can greatly decrease the amount of communication. I don't have results for this here. We do have a paper on it where we added it into Hypre, and we do see very large improvements, but I'm currently adding it into RAPtor, and so I'm not showing anything with node-aware communication right now for this. So finally, a little bit about RAPtor. This is our parallel AMG solver. It's written in C++ with MPI. It's based off of PyMG, and so we wanted to write it so that was very simple and readable. It, in style, looks very similar to PyMG, but we wanted to add this node-aware communication. And so I'll show some results versus Hypre. It outperforms Hypre in both the performance and the scalability outside of a very small number of processes. But once you go past 100 or a few hundred processes, it does outperform Hypre. So this shows for both the setup and solve phase of an anisotropic diffusion problem. The blue line here are Hypre timings, and then all of the other lines are these different RAPtor timings. So the green line is the standard classical AMG in RAPtor. This is performing the exact same methods as Hypre. If we use Hypre's the same random number generator as Hypre, we can actually get the same residuals for many problems. And so we are doing the same methods. It's just a different implementation. And so you can see that there's a drastic difference at times between the blue and green timings. And then the red timings are that standard AMG and RAPtor, but with node-aware communication. The purple lines are using that smooth aggregation solver, and then the yellow line is using the node-aware communication inside of smooth aggregation. This shows for anisotropic diffusion. Again, this is the total time together for anisotropic diffusion and Laplacian. So the Laplacian hierarchy here is also using the aggressive coarsening in both Hypre and RAPtor. So these are the parameters. Again, we see large improvements to both the scalability and performance in the best case typically using node-aware communication inside smooth aggregation solvers. So that all showed everything has been strong scalability. We also do see speedups for weak scalability. So if we look at a problem with 10,000 degrees of freedom per core, but scaling out to 8,000 processes, we see pretty similar results. So in summary of this, we've currently released version 0.1, and so it's still very in progress work. It's on this website. We're currently adding a PETSI interface to this, so we would like to be able to use it with PETSI. However, we've been working on this on and off for a little bit. We've been talking to Jed. We're currently looking at how Trilinos interfaces but it's been taking a while. If anyone, this seems like the right crowd, if anyone here has experience with interfacing different applications with PETSI and would like to give me some advice, that would be very helpful. We're also currently adding documentation and cleaning the code. If you go on GitHub right now, there is no documentation. So I have added a few slides to the end of this end of the slides here. And I've also put them on my website. And so if you click on my name and want to see them, you can use RAPtor. It is standalone before we get the PETSI interface and documentation, if you'd like. So some future work that we're looking at, we currently have a new performance model. It's updates to the standard alpha, beta, and max rate models that added in both penalties for both contention, network contention, and the queue search times. And so if you look at the time for sparse matrix vector multiplication on each level of the AMG hierarchy, you can see that there are, or that a large amount of the time is spent in the queue search. So this is this makes a lot of sense that node-aware communication does so well here, because the queue search time is very dependent on the number of messages. And so because node-aware communication greatly reduces the number of messages, we see very large speedups. And it's most likely due to the fact that we're reducing queue search time. And so anyhow, we have these updated performance models. We would really like to use them to try and figure out when we should be using node-aware communication. Because we don't want to use it on every level, we don't always want to use it on every operation. And so we would like to be able to predict when we should turn it on and when we should turn it off throughout our solver. We also have the same model for matrix-matrix multiplication. And you can see it looks quite a bit different. So the majority of the time here is actually spent with network contention rather than queue search time. And so we do not see as large of speedups with matrix-matrix multiplication compared to the SPIMBs. And this is most likely because we don't totally reduce network contention. So we would also like to look at extending node-aware communication to groups of nodes. So aggregating among groups of nodes rather than on a single node to try and reduce this contention. And so that's my talk. There are a few slides after this that I'm not going to go over, but on different methods in RAPtor if anyone's interested. So are there any questions?
Thank you, Amanda. Any questions?
So on node, we're still doing regular message passing. We're not using shared node.
No, right now we do have regular message passing. We have a research scientist that has been working on adding in the MPI shared memory. And he has shown that we can, for just the standard SPIMB, we can further speed it up. We assume it should be able to greatly improve this operation since there's so much more on node communication, but we don't yet have it in there. Yeah.
So, have you given any thought to splitting off the communication or making that sort of separate library that it's used generally?
Yes, so we actually are writing a library right now, just a lightweight MPI library that just does the node-aware communication for any application. So it just has an MPI init and then MPI send, MPI receive. It's not finished yet, and so it's not online, but we are in the process of doing that. Yeah.
The hardware performance, that's actually AMG.
Sorry?
Performance figures, I assume that's comparing Hypre with AMG.
Yes, it's using Boomerang.
214 or older version.
Sorry?
Is that 214 or older version?
So it's, when I made these, it was the most recent version that had been released. It's possible that a newer version has been released in the past couple months. I'm not entirely sure. If they released it in March, I might not be using that one. I'm not entirely sure. Do you know, should that change performance?
I don't think they made any performance figures with AMG side.
Okay.
Most people do.
Okay. So we've run out to, I've done runs out to 100,000 cores. It was a while ago though, so things have changed. We just added in the smooth aggregation. So I've only gone out to 16,000 cores right now with the smooth aggregation solver. The weak scaling has stayed very consistent.
So thank you, Amanda, again. Do we have a next speaker? See, I'm not sure how to. David, do you know where?
Oh, sorry.